Okay, Bismillahirrahmanirrahim. Assalamualaikum and a very good morning. So, thank you for joining this online class. I'm so sorry. I have a bit of transportation problem. So that's why I cannot reach the campus this morning. And therefore, we need to do this class online. So, we will continue on our next part of chapter 3. As you have already know, that we have two parts of chapter 3. So the first part we have already covered, which is work and energy. So the second part will be impulse and momentum. So let's take a look at what does it mean, impulse and momentum. So anyone knows what impulse mean and what is momentum? Siapa tahu impulse tu apa, momentum tu apa? Any idea what this means? Let's go to impulse first. What is impulse? Have you heard of this word before? I think you should have learned this in physics, for example. Any idea what impulse is, or how do you calculate impulse? Okay, so basically, previously in the previous topic ataupun part of chapter 3, which is work and energy, we have work done, which is the force multiplied with the distance. So previously we have work, which is equal to force times distance. This is the easiest way to describe work done lah, ataupun work done. Let's call it work done here. So work done is force times distance. So when we talk about impulse, it is almost similar to work done. So impulse is basically equal to force times the time taken. So basically, we are talking about force in Newton. So the unit for force is in Newton, multiplied with time, which is in second. So the unit for impulse will be Newton second. Okay, this is what it means by impulse. Whereas for work done, we have the force in Newton, okay, and we have distance in meter, and the unit for work done will be joule. Okay, the unit for work done is joule. So this is basically what it means by impulse. So impulse is force multiplied with time. Okay. Next, we have another term which is called the momentum. Okay, the momentum. So any idea what momentum is? Previously, we have energy or kinetic energy. Previously, we have kinetic energy, which is given by the formula 1/2 mv square plus 1/2 ig omega square. Let's make this smaller. Okay, 1/2 ig times omega square. This is the general formula for kinetic energy. And for momentum, it is basically equal to the force. Momentum, is the mass times velocity. This is for linear momentum lah. This is linear momentum, which is basically equals to m times v. Vg lah, the v of the center of gravity. This is linear momentum. We also have angular momentum. Okay, remember in rigid body, we do not only have object that is translating left and right, up and down. We also have object that is rotating. So in the case of angular momentum, momentum, this will be equal to the mass moment of inertia, IG. Okay, remember the sibling of mass. If linear is mass, then for angular it will be mass moment of inertia, which is IG lah. So if the linear is velocity, then the angular component will be IG times omega. Okay, IG times omega. So now you have impulse, which is force multiplied with time, and we have two types of momentum, which is mass times velocity, and also angular momentum, IG times omega. Impulse also, we have the angular impulse. This is linear impulse. This one is linear impulse. So if the angular impulse, this will be equal to force. For linear is force. Therefore, for angular, this will become moment m, and multiplied with also with time t lah, with time t. Right. So we have linear impulse and also angular impulse. Okay, so this is basically the definition of impulse and also momentum. So in short, or to easily understand, impulse is basically force darab massa, force multiplied with time, whereas momentum is the mass times velocity, or in angular term is the IG, mass moment of inertia, multiplied with omega, which is angular velocity. So this is basically impulse and momentum. Okay, next, let's see how can we derive the equation that we can use when it comes to impulse and momentum. So let's go back to what we have learned in chapter 2, which is the equation of motion, which is the Newton second law of motion. So we have F equals to M times A. This is our basic equation of motion lah. Basically is the total force, is the sum of force. Sum of force is equal to M times A, and A is basically the acceleration of center of gravity. So AG lah, F equals to M times AG. Okay, this AG here is basically the change of velocity over time. So we can write this also as the change of velocity of center gravity, dVg over dt. This is equal to A lah. And we can then bring all this, the previous term down also. So we have total force is equal to the mass times dVg over dt. Okay, what we can do here is we can bring this dt to the left-hand side. Okay, to the left-hand side. So when we bring this to the left-hand side, what we will have is now total F dt is equal to M. We can also multiply this M here into this Vg, combine them together. So we will get D is in front, D, and then we have M times Vg. We just combine them together. Okay. So let's write this dt and d in different color. So this will be dt here and d in front of the mvg. Okay, so how do we get rid of this d in front? Is by integrating the equation lah. So when you do integration, what we can do is we can put integration here, and then when we put integration on the right hand side, we also need to put integration on the left hand side as well. So when you put integration, this d will be gone. Okay, this d will be gone. Same goes for the integration lah. They will cancel out each other. So when you put integration, basically these two terms will be gone. Okay, so what we have left is now the integration on the left hand side. So in the end, what we will get is, we will get on the left hand side is integration of total f dt. Okay, and because we have dt here, so this will be taken from t1 until t2 lah. We are now talking about the change of apa ni, the change of time, duration of the motion. So the motion will take place from t1 until t2, and then this will be equal to before that. Okay, before that, the change dmvg here, this also can be written as the change of mvg. This means m is unchanged, but vg will be vg2 minus mvg1. Okay, that is what it means by the change of velocity. So the change of mvg. So the change means change from the apa ni, the first position ataupun first time, the time number 1 into time number 2. So what is changing is the velocity lah. The mass is not changing. So then when the integration and the change d is cancelled out, then what is left on the right hand side is m times vg2 minus m times vg1. So this will be the equation for linear impulse and momentum. This is the equation for linear impulse and momentum. We call this as the principle of, we call this as the principle of linear impulse and momentum. Okay, this is on the left hand side here, we have linear, on the left hand side we have linear momentum, linear impulse. It is the force times time, linear impulse. And on the right hand side, these two is the momentum. This is momentum number 2. This is momentum number 1. So this will be linear momentum. Okay. So taken from this, what we can do is, I will take this and bring it to the next page. Okay. Okay, so by looking at this, if you remember, in the principle of work and energy, in the principle of work and energy that we learned before, work and energy, we have the equation T1, initial kinetic energy, plus the total work done, total U, is equal to T2. This is the principle of work and energy. Okay, we can do the same for the principle of impulse and momentum. So therefore, the principle of impulse and momentum, the principle of impulse and momentum, okay, what we can do is, first we can take this part here, negative mvg1, and bring this to the left hand side. So what we have then is m times Vg1, and then we have plus the integration of total force dt is equal to m times Vg2. Okay, so what is this? This is basically mvg1. mvg1 is the initial impulse. Okay, so what this means is this is initial momentum. Initial momentum plus when you integrate f dt, that will be the outcome, the output will be force darab time lah. Force darab time is the linear impulse. So if you look here, force darab time ni is the linear impulse. So initial momentum plus the total impulse, total linear impulse is equal to the final momentum. All right. So this will be the principle of linear impulse and momentum. So I forgot the word linear here. Let's put it here. The principle of linear impulse and momentum. Okay. So the principle of linear impulse and momentum is basically similar form to the principle of work and energy. Kalau principle of work and energy, initial kinetic energy plus total work done is equal to the final kinetic energy. But the principle of linear impulse and momentum is the initial momentum plus the total linear impulse is equal to final momentum. Okay, dia konsep dia hampir sama, cuma the content is different lah. Okay. Any questions so far? Any question on this? Okay. So next, we will do the same for the angular. So remember, previously I mentioned about we have linear impulse and also we have angular impulse. Same goes for momentum. We have linear momentum and also we have angular momentum. So before we go to the angular component, which we will do the same derivation here, let's have a 2-3 minutes of break because I need to go to the toilet, and then we will continue after that. Okay, so we'll have a 3 to 5 minutes break and then we will continue at about 9 a.m. Okay, see you guys in 5 minutes. Okay, let's continue, shall we? Okay, so previously we talked about the principle of linear impulse and momentum, which is pretty similar to the principle of work and energy. So for the principle of angular impulse and momentum, it is also similar to the principle of work and energy. So I will copy this and write it in the next page. So we see that the principle of work and energy is like this. So when it comes to the apa ni, angular punya component, so now we talk about the principle of angular impulse and momentum. Tadi principle of linear impulse and momentum. Okay, so previously the linear component comes from F equals to ma. So now the angular component will be mg. The total mg is equal to ig times alpha. So this is where it starts lah. Okay, mg is equal to ig times alpha, and alpha we can write this as ig times alpha can be changed to d omega over dt. Okay, alpha and d omega over dt is the same. And then we can do the same thing. We bring dt to the left hand side, and then this will become ig times d omega, ig times d omega, meaning that d omega is omega 2 minus omega 1 lah. D means the change. So when we talk about change, what is the change of angular velocity? Meaning that angular velocity yang kedua mesti tolak angular velocity yang pertama. So that is, we get the change lah. If we talk about the change of velocity, means that velocity yang kedua tolak velocity yang pertama. What is the difference? Itu maksud dia D. The small d here. Okay, if we zoom in, d here means the change. The change of something lah. D is the change of something. So dt kita dah bawa ke sebelah kiri. So now we have total mg dt. Dt ni dah pergi ke sebelah kiri is equal to ig times omega 2 minus omega 1. Okay, and then bila kita ada dt sebelah kiri, we need to put the integration punya sign lah to the left hand side, so that this will be integration from t1 to t2. Okay, and then finally the equation akan jadi integration of t1 to t2 mg dt is equal to ig omega 2 minus ig omega 1. So kita multiply lah ig with the omega in the bracket. So finally, we will do the same like what we did previously, which is to bring this ig omega 1 to the left hand side, and we will get the same principle similar to the principle of work and energy that states ig omega 1 plus the total the integration of mg dt is equal to ig omega 2. Okay, so this is basically the principle of angular impulse and momentum. Okay, so the principle here states that this will be, if I zoom in, this will be the initial, sorry, This will be the initial angular momentum. Initial angular momentum. Okay. Plus the total angular impulse is equal to the final angular momentum. Okay. So basically it has the similar, what do you call, similar format lah kepada principle of work and energy. Principle of work and energy, T1 is T1 plus total U. So this is basically initial kinetic energy plus total work done. Total work done is equal to final kinetic energy. Okay, final kinetic energy. So dia sama konsep. Kalau principle of work and energy, initial kinetic energy tambah total work done is equal to final kinetic energy. For principle of angular impulse and momentum, initial angular momentum plus total angular impulse is equal to final angular momentum. Kalau principle of linear impulse and momentum, initial linear momentum, semua ni jadi linear lah. This will be initial linear momentum plus total linear impulse is equal to final linear momentum. Okay. Okay, so now let's look at, before we compile all the equations that we have and then try to solve some problems using that equation. We will look at this. Okay. Remember, we have three types of motion: translation, rotation, and also general plane motion. And the linear momentum is normally labeled as L. Okay, is labeled as L. And this will be equal to m times vg lah. Momentum is mass times velocity. This is linear momentum. Angular momentum, on the other hand, angular momentum, okay, is labeled with the symbol H. Okay, H. And it depends on where the moment is calculated. So kalau dia calculated at point G, then we write it as Hg lah. Hg, this will be equal to Ig times omega. Okay, so we have now two new terms ataupun symbol lah to understand, to know, which is L for linear momentum and H for angular momentum. So when it comes to translation motion, translation only motion, then we have L equals to m times vg. Okay, untuk linear. Whereas Hg is equal to 0 lah, sebab there is no rotation dalam apa ni, dalam translation. And then when we talk about rotation about fixed axis, kalau you refer to this figure here, then we have L is equal to m times vg, okay. And we also have Hg, which is equal to Ig times omega. And also, if we want to calculate about point O, the moment, then we have another equation, which is HO is equal to IO times omega. So it depends lah. Kalau kita calculate about point G, kita akan guna Ig times omega. Tapi kalau kita calculate about point O, the formula will become IO times omega. And of course, when you want to calculate IO, you have to use the parallel axis theorem lah. Okay, so that is translation and rotation about a fixed axis. And another one is for general plane motion. General plane motion pun sama. We have apa ni? We have the L also. General plane motion consists of both apa ni, translation and also rotation. So we have L equals to M times VG untuk general plane motion. We also have HG, which is equal to IG times omega. And for general plane motion, if we can locate the location of IC, ini adalah location of IC lah normally somewhere, whether it is inside the body ataupun outside of the body. So we can also calculate HIC if we know the location of IC, which is equal to IIC times omega. Okay, and then to calculate apa tu IC punya IIC, mass moment of inertia about IC, you need to use the parallel axis theorem lah. Okay, so basically this is the three situation that we have lah. Okay, let me add one more page before we go to the next. Okay, so now we will compile the principle of impulse and momentum. So previously, kalau kita go back to this, we have this green punya equation, the principle of linear impulse and momentum, m Vg1 plus total plus integration of f dt, which is the total impulse lah. Integrate, when you integrate force with respect to time, you akan dapat force darab time lah, equal to m Vg2. Okay, so this can be written in two axis. Okay, linear motion ni can be in x-axis, can also be in y-axis. So we can write this equation in two axes. So let's copy this and transform this into two axis punya equation. Okay, so let's go to the page here and paste this. Okay, and then I'm going to paste another one. Okay, so what is the difference here is that we can write this one in x-axis. So this will become m VGX1. Okay, m VGX1, and this will be fx dt, and at the back will be m VGX2. Okay, so ini hanya dalam x-axis sahaja. So this will be x-axis. Okay, so that is the first equation. So this will be equation number 1 in the principle of impulse and momentum, where we write the linear principle of linear impulse and momentum in x-axis. For equation number 2, we can write the same equation now in y-axis. So this will become mVgy1, this will be fy dt, and this will be mVgy2. Okay, so this will be in y-axis. Okay, so now we have two equations for the principle of impulse and momentum in linear motion. So we have x-axis equation, and also we have y-axis equation. And the last equation is taken from the angular lah, principle of angular impulse and momentum. So let's copy this, right? And then we'll paste it here. Okay, so this will be the third equation. This will be equation number 3, which is the angular punya component lah. So this will be the angular component. Okay, so meaning that the principle of impulse and momentum ni ada 3 equation. Kalau kita recall balik, here let's write it as recall Okay, kalau for linear, for apa ni, work and energy. Sorry. Okay, so if we recall the principle of work and energy, principle of work and energy, we only have one equation, which is T1 plus total U to move from position 1 to position 2 is equal to T2. This is the principle of work and energy, only one equation. But for the principle of impulse and momentum, okay, for the principle of impulse and momentum, we have three equations to use. Not necessarily you have to use all the equations. It depends on the situation lah. Kalau motion tu hanya berlaku dalam x-axis, for example, then you only use the principle of impulse and momentum in x-axis. If the motion is only involve rotation motion, then you only use the principle of impulse and momentum for angular. So that is the difference lah, slight difference between principle of work and energy and the principle of impulse and momentum. So work and energy, only one equation that you can use. However, for the principle of impulse and momentum, you have three equations. One in x-axis, one in y-axis, and the other one is for the angular component. Okay, so let's look at a few examples so that you can understand how to use the equation lah. Okay, let's read the first problem here. 60 kg wheel has a radius of gyration about center O, KO equals to 300 millimeters. So by reading the first statement, you know that this is a non-homogeneous object. Okay, so from here, we can, when you, in the test, for example, when you read the first line, you straight away, what you can do is to calculate the IO lah in this case, because the center point is called IO. IO is equal to M times KO square. Okay, so M is 60, KO convert into meter, it will become 0.3 square. Therefore, we have IO equals to, what is IO here? 5.4 kg meter square. Okay, so we have the first information that we need later in the calculation, which is IO equals to 5.4 kg meter square. Okay, if it is subjected to a couple moment, okay, now another clue, there is a couple moment M, which is M equals to 3T square Newton meter. Okay, moment now is given as a function. What does it mean? It means that as the time increase, the moment also increase. Okay, meaning that moment dia bukan satu number yang fix. It is not like 100 Newton meter. It depends on the time. So when t equals to 0, the moment is equal to 0. When t equals to 1 second, the moment will be equal to 3. 3 times 1 square. When time equals to 2 seconds, the moment is equal to 3 times 2 square. 3 times 4 will be 12. Okay, when the time is equal to 3, then moment will be 3 square is 9. 9 times 3, 27. So meaning that the moment keeps changing as the time change. So this is what we call a variable moment. Okay, it is not a fixed or a constant moment. Okay, so what do you want to determine here? Determine the angular velocity. Okay, still what we want is omega. We want to calculate omega when t equals to 4 seconds. Okay, this is the difference. This is how you determine whether you should use work and energy method, or impulse and momentum method to solve this problem. Now, this involve time. Kalau dalam soalan work and energy, you remember, I think there is a similar problem to this in the work and energy. Dia akan tanya determine angular velocity after it has rotated 20 revolutions contohnya. So 20 revolution punya rotation is involve distance. Jadi bila dia tanya something related to distance, then you know that you should use work and energy. Tapi bila dia tanya determine angular velocity pada masa 4 seconds, time equals to 4 seconds. So anything that relates to time, straight away you should know that you have to use the impulse and momentum method. So dekat mana yang membezakan adalah dekat apa condition yang dia bagi. Okay. Determine angular velocity sama. Dalam work and energy also you have to determine the angular velocity. Tapi angular velocity after dia roll 2 meter contohnya. So ada distance kat situ. Or after it has rotated 10 revolutions. Jadi ada angular punya distance dekat situ. So as compared to here, angular velocity after 4 seconds. Jadi ini definitely will involve impulse and momentum method. Okay, so how do we solve this? Let's go back to the equation that we have. So we have 1, 2, 3 equations. Okay, we have 1, 2, 3 equations. Tak perlu tengok yang bawah ni. Ni adalah just a comparison to what we learned previously. So we have equation 1, equation 2, equation 3. So when you refer to the question here, apa yang dia nak you calculate adalah angular velocity. So by referring to equation 1, equation 2 and equation 3, you can see that angular velocity only appear in equation number 3. Jadi, and then looking at this motion also, object ni rotate macam ni, and the rotation, the object will stay in this position. Dia hanya rotate saja. So basically there is no motion in x-axis, there is no motion in y-axis. So the motion only occur at point O and rotating around point O sahaja. Jadi what we can do here is we will use the third equation only to solve this problem. So let's copy this equation and bring it to here so that we can use this to solve the problem. So this is the equation that we have, which is the principle of angular impulse and momentum. And let's use this equation to solve the problem. Okay, so we need to change this a little bit because in this case, center point is called point O. This is the center point and it is called point O. Jadi kita kena tukar this equation to become O lah, IO, IO and also MO. So let's erase this G here, okay, and change it to IO, MO, and also IO omega 2. All right. Okay. So how do we solve this? Now, let's go component by component. Okay. The first one, there is another clue here where it says starting from rest, meaning that initially the wheel is not moving, and then the moment is applied, then it starts to roll. So when it says starting from rest, we know that omega 1 is equal to 0 because starting from rest. Okay, starting from rest. Okay, so bila omega 1 0, then the whole thing on the left hand side, IO omega 1 tu akan jadi 0 lah. So this part here is equal to 0. Okay, settle. And then IO kita dah calculate tadi 5.4. What we want to calculate actually is this lah. Omega 2 is the one that we are interested to find. Omega 2, angular velocity after time t seconds. Okay, now what we need to pay attention to is this middle part. Okay, this middle part. Integration of MO dt. Okay, so let's do that. So integration of MO dt kita nak integrate daripada apa ke apa ni. So daripada time is equal to 0, time mula-mula 0 to 4 lah. Okay, time equals to 0 to times time equal to 4 seconds. And then MO is basically 3t square dt. So this is the integration that we are involved in. So this will be, when you integrate 3t square, dia akan jadi apa? 3t square. Dia akan jadi 3t square tu dia akan jadi 3, 2 plus 1, and then divided by 3 also. Okay, so here you can cancel this, and this will be t to the power of 3. Okay, t to the power of 3. T to the power of 3 from 0 to 4. Okay, so now we put in 4 in the t first. So this will be equal to 4 to the power of 3 minus 0 to the power of 3. Okay, this I hope you know how to do the integration lah. Okay, so 4 to the power of 3 minus 0 to the power of 3. So what do you get? 4 to the power of 3. 4 cube. Dapat apa? 4 cube. Let's calculate it here. 4 cube will give us 64. Okay, so 4 cube will give us 64, and 0 to the power of 3 is 0 lah. So 64 we get here. And then finally, what we can do is to put all them together. Okay, from this equation, from IO omega 1 plus integration of MO dt is equal to IO omega 2. Omega 2 is the one that we want to find here. Okay, so this part is equal to 0. So we know that this is 0 plus 64. 64 is MO dt is equal to IO is 5.4 and then omega 2. And therefore, from here, we get the value of omega 2, which is equal to 64 divided by 5.4, which will give you 11.85. 11.85 radian per second. Okay, so this will be the final answer lah for this one. Okay, any question on this? This is how you solve problem related to impulse and momentum. Any question? Okay, if there's no question, let's move on to the next one. Okay, the next one, I will share the notes here and also the recording later in the WhatsApp group. So let's read this question here. If the previous question involves rotation about fixed axis, this one is general plane motion. Okay, this is GPM. Sorry, this is GPM. Okay, how do we know that this is GPM? You can see the wheel is rolling, so therefore there will be a apa tu translation forward, and also there will be rotation lah. Okay, 300 kg wheel has a radius of gyration about its mass center, KO 400 millimeter. Okay, so when we see this, we know that this is a non-homogeneous. Straight away we can calculate IO. Okay, macam saya buat tadi, IO is equal to M times KO square. Okay, so this is equal to 300 times 0.4. 400 millimeter, you convert to meter, it will be 0.4. 0.4 square. So therefore, kita akan dapat IO is equal to 300 times 0.4 square, which is 48 kilogram meter square. Okay, so that is our IO. Okay, first step kita dah selesai. If the wheel is subjected to a couple moment M 300 Newton meter. Okay, so now the moment applied is a constant moment ataupun fixed punya moment, bukan lagi variable moment macam soalan yang tadi. Okay, now determine angular velocity. Ini yang kita nak calculate, angular velocity 6 seconds. 6 seconds after it starts from rest. Okay, jadi masih lagi kita tahu that this problem involve impulse and momentum sebab dia tanya angular momentum 6 second after. Bukannya 6 meter after it has roll 6 meter. Itu distance. Bila dia involve distance, kita tahu kita perlu guna work and energy. But in this case, it involves time, so you have to use the impulse and momentum method. And it says starts from rest, okay, and then no sleeping occur. Okay, so ini semua adalah clue. Okay, so when it says no sleeping occur, straight away we know that the contact point here is the location of IC. Okay, bila no sleeping occur, the contact point is the location of IC. Okay, so ada beberapa perkara yang kita perlu determine here. One is the angular velocity yang kita nak kena cari. And then we also need to determine the friction force. Okay, dia nak tahu juga friction force that develops between the wheel and the ground. Okay, so to solve this, the first step is let's draw the free body diagram first. So free body diagram, we will have a weight here, mg, pointing down at the center of gravity. We have the normal force. Let's erase dulu IC ni. Okay, let's erase IC first. And at this contact point, there will be a normal force NA. And we will also draw that this is the location of IC here. Okay. And then we have friction. Of course, we have the moment here. 300 Newton meter moment. Okay, ini moment is also a force lah. And then we have a friction which is pointing forward. Friction pointing forward because the rolling is occurs in clockwise direction. Jadi friction akan oppose the rolling motion lah. So this will be friction. Let's call it FR. We will calculate the friction later. Okay, so this is basically the free body diagram. So we have 4 forces lah acting on the wheel right now, which is the weight, the normal force, the moment, and also the friction force. Okay. So first, we need to calculate the angular velocity. Jadi, to calculate angular velocity, if you go back to the list of equation that we have, angular velocity definitely comes from the third equation. Jadi kita akan gunakan the third equation dulu first to get the angular velocity and see whether we can get the angular velocity from here lah. Okay, so let's write down the third equation first. Okay, the third equation is we have IO in this case. So IO omega 1 plus the integration of MO dt is equal to IO omega 2. Okay. Yang mana yang kita nak cari? Yang kita nak cari adalah omega 2. Okay. And then it says starting from rest, meaning that omega 1 is equal to 0. So we know the first component ataupun first part of the equation tu adalah equals to 0. And then MO dt ni time 6 seconds. So we know the integration starts from 0 until 6 lah. Integration starts from 0 until 6. Okay. So let's focus on the integration punya component dulu. Yang tengah ni. So, kita ada integration from 0 to 6 MO now. So let's look at the moment. So now we want to calculate moment dekat mana? Dekat point O. So we also need to define the positive direction lah. So when it comes to rotation, kita kena define positive direction. Jadi kita pilih direction of rotation as positive, which is clockwise punya rotation lah. Okay, now bila kita calculate pada point O, where is point O? Point O is in the middle here. Point O is basically point G lah. Okay, so what do we do? As usual, we will draw a line dekat point O. Okay, draw a line dekat point O, vertical and also horizontal line dekat point O. Okay, like that. So line yang the force that falls on the line will not have any moment about point O. So by looking at this, you should see that MG has no moment, NA has no moment. So the only force that has moment is the moment itself, M ada moment, and also the friction. Okay, so now friction will be multiplied with the radius lah. Radius. Friction will be multiplied with the radius here. Okay, the distance daripada friction to the line, which is 0.6 meter in this case. And to go to point O, it will be in the negative punya direction lah. So this will be going this way. So negative direction. Okay. So what we write here is basically we have 300 the moment tu tak payah nak darab dengan apa-apa distance lah, because it is already a moment. 300 and then put it in bracket, and then we have minus because the friction punya moment is negative untuk pergi ke point O. Friction times 0.6. Okay, friction times 0.6. So let's saya padam bracket ni, and let's put a square bracket. Okay. Alright, so this is what we have, integration of the moment. Okay, because the moment we have now the 300 Newton meter moment, and also friction will also have a moment. So what happened when you integrate this moment, 300 and also 0.6 FR ni, you integrate. So what will happen is you will get 300 times 6. Okay, sebab 300 ni dia akan multiply dengan time lah. Time tu daripada 0 ke 6. So 300 darab 0 lah. 300 darab 6 dapat 300 darab 6. And then minus, now you have friction times 0.6. Also you multiply with 6. Sebab kita punya apa tu? Kita punya integration tu daripada 0 ke 6. Okay, so what you will get here is 1800 daripada integration ni minus minus 0.6 times 6 is 3.6 FR. 3.6 FR. Okay. So ini hasil daripada integration. Okay, now kita akan substitute everything ke equation yang di atas. So now the first component will be 0 plus 1800 minus 3.6 FR. Yang ini you dapat daripada integration of MO dt is equal to IO, kita dah calculate, 48 and omega 2. So here you can see that we cannot solve this problem yet sebab kita ada dua unknown dalam ini, which is friction and also omega 2. So let's rearrange this equation. Kita bawa 3.6 FR to the right hand side, and this will become 48. This will become 48 omega 2 plus 3.6 FR is equal to 1800. Okay, so kita ada satu equation yang kita belum boleh solve because dia ada dua unknown. Okay, so kita terhenti di sini. Now we need to find a way to get another equation. So bila kita ada dua unknown, we need to have two equations to solve the problem. Okay, so now looking at the motion again, the motion will involve rotation and also translation to the right. Jadi kita akan pilih the equation from this the x-axis punya equation to use because the motion is in x-axis. There is no motion in y-axis. So kita akan pilih x-axis punya equation. Okay, so let's write down this equation for x-axis to proceed. Okay, so equation for x-axis we have m times vx1. Let's write it as vx1 lah. It's actually vgx1 lah. Vx1 ataupun kita tulis dia penuh lah. vgx1. Okay, and then plus the integration of fx dt is equal to m times vgx2. Okay. Bila dia kata starts from rest, meaning that vgx1 is also 0. Dia tak ada motion pada awal. Okay, vgx1 is also 0. Okay, now let's go to fx dt. Okay, fx dt. Let's focus on this part. Okay, now kita nak integrate daripada 0 ke 6. 0 to 6 fx dt. So zoom in to the free body diagram and look force apa yang ada dalam x-axis, and it turns out only friction force that is acting in x-axis. Jadi apa yang kita buat adalah kita integrate friction force lah, Fr dt. Tak perlu nak multiply dengan radius because this is not a moment, this is a force. Okay, so integrate Fr dt. So what do you get when you integrate Fr dt from 0 to 6? You get Fr darab 6 lah. Fr darab 6 minus Fr times 0, which is 0 lah. So tak perlu nak tulis. So we have here Fr times 6. Okay, last kali on the on the right hand side here, M ni kita dah ada, M is 300. Now VGX2. Okay, VGX2 kita tak ada. VGX2. Okay, so bila kita zoom in here, dekat mana VGX2 ni? VGX2 ni is basically here. This is basically VO lah, bukan VG. VO. This is basically VOX2. Okay, VOX2. Okay, so sebenarnya kat sini pun kita kena tukar lah. Kita kena tukar ni kepada VO. So this will be bukan X. VOX. VOX1. And this one is also VOX2. VOX2. Kenapa kita tukar? Because center point dia dipanggil sebagai O. So VOX2 is here, and because we know that this is no slipping punya rolling, no slipping occur. So kita tahu that the center bawah tu adalah IC. So we can then use the equation V is equal to omega times R to represent VOX2. Okay, dia seolah-olah point IC tu adalah dia punya dia punya rotation point lah. So dia seolah-olahnya seperti if we draw, this is the point O and this is VOX2. Okay, and then we have the link to here, and dekat bawah ni IC ni adalah dia punya seolah-olah dia punya fixed point lah. So this is basically bawah ni adalah IC. Okay, so as if this thing is rotating about the center point IC, about IC. So we can use the V equals to omega R here, and therefore VOX2 is equal to omega 2 times R, which is 0.6 times 0.6. Okay, so we can use this here. VGX2 is basically equal to 0.6 omega 2. Omega 2 tadi yang kita nak guna lah. Omega 2 tadi yang kita nak guna. Okay, so taken everything from here, kita boleh rewrite kita boleh substitute all the values. So the front part will be 0 plus 6FR, 6FR, okay, equal to M is 300, M is 300, VOX2, sorry, this one should also be written as VOX2. Ya, ini adalah VOX2. Okay. 300, M is 300 times 0.6 omega 2. Okay. So then kita boleh susun lah ini. Kita boleh susun dia. Ataupun kita boleh keluarkan FR daripada sini. So therefore, FR is basically equal to 300 times 0.6, 300 times 0.6 sebelah kanannya divided by 6, which is 30 omega 2. So FR is basically 30 omega 2. Okay, so now we have another apa ni clue here. So we can then substitute this in this equation. Okay, we can substitute FR equals to 30 omega 2 dalam equation ini to solve this, and therefore we will get 48 omega 2 plus 3.6. FR tu adalah 30 omega 2, okay, is equal to 1800, and therefore we will get the value of omega 2 is equal to 48 plus 3.6 times 30, 156, and then 1800 divided by 156, you will get omega 2, which is equal to 11.54 radian per second. So this will be the first answer. Okay, this is the first answer for the angular velocity. And then therefore we can also calculate FR from here. FR is then 11.54 multiplied with 30. So we will get FR is 346.15.2 lah. 346.2 Newton. This will be the friction force. Okay, so we have solved the problem lah by using the principle of impulse and momentum. So in the first question sebelum ni, kita hanya guna satu equation sahaja, which is the third equation yang ini, and we get the answer. But in the second punya equation, second punya question, second punya problem, we need to use two equation, which is this one and also this one in x-axis. So although we have three equation, it is not necessarily that you have to use all three. Sometimes you use one to solve. Sometimes you have to use two to solve. Okay. Any question so far on the topic before we end the class? And we will continue a few more tutorials on Monday next week lah. Any question so far? Okay, so if there's no question, I think that will be all for today. Thank you for joining the class online. I apologize for the short notice this morning that we need to do the class online. I will share the notes as well as the recording in the WhatsApp group later. Okay, so I will see you again on Monday next week. If required, then probably we're going to have another replacement class online before you sit for the test on Wednesday lah. Maybe if apa ni, kalau ada keperluan, maybe we will do the online class on Tuesday, just to do a few more example problems lah before you sit for the test 3 on Wednesday. Okay, thank you, and I will see you again on Monday next week.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Doktor.